Okay, up to this point, what do we know? Well, light had to act like a wave, it had to act like a particle, and so we're forced to accept it can act as both a wave and a particle. And this is the beginning of quantum mechanics, okay? But it really hadn't taken fully off yet. Scientists were in agreement about this weird behavior of waves. What's going to happen next is really going to push us into the world of quantum mechanics. This is going to be the beginning of what is often called the quantum revolution. So along comes a Dutch aristocrat named Louis de Broglie. Louis de Broglie was a student, actually. He was a PhD student. He was studying physics. So when he went to get his PhD in physics, his doctorate, right? So you may or may not know this. When you want to go to get your PhD, you have to present your thesis, okay? Essentially, your new idea that you're speaking into existence in this universe. This kind of question that you're going to try to answer, and then your argument for it, and your research and all of that, okay? And then when you do that, you have to defend it to a panel of experts, to a panel of other PhDs who then make you defend your thesis. Okay, it sounds kind of scary, honestly, but Louis de Broglie was doing this. He wanted to become Dr. de Broglie. And so for his PhD thesis, his question that he was asking was clearly, undeniably, waves do sometimes act like particles. Light sometimes does act like a particle. So he essentially made an argument of symmetry. He said, well, hang on, if waves are acting like particles, then they kind of are particles. And these particles can sometimes act like waves. So does any old particle act like a wave? So de Broglie kind of arrived at this question. And in his thesis, he made this argument. He said that the answer is yes. And his reasoning is now known as the de Broglie hypothesis. And it was going to change things forever. When he went to defend this thesis, the panel of experts, the other PhDs that saw it, thought it was nuts. Okay. It was so nuts that they almost considered saying, no, you do not get to get your PhD. In fact, they kind of did. They kind of threw it out. They said, no, de Broglie, forget it. Okay. But they couldn't really find any problems with his thesis. They said, it's just wrong. There's no way. But when they looked at his reasoning and all his arguments, they said, I don't know. We're not finding an issue here necessarily. He's made a good point. And so they said, well, it seems crazy. No PhD for you. But let's just in case, this sounds up Einstein's alley, who was unknown before the photoelectric effect, but now was very famous, very well known, very well respected. So they sent it over to Einstein. So upon reading de Broglie's hypothesis in his thesis, Einstein said that it was, quote, the first glimmer of light in the darkest of our physics enigmas. Okay, he went on to say that de Broglie had lifted a corner of the great veil, this veil being something concealing the nature of reality, right? Einstein loved de Broglie's hypothesis. It made a lot of things click that at the time we were panicking, right? Everything seemed to be wrong. Everything was, in a way, wrong. All of this Newtonian classic physics broke down. It worked for describing the stuff we see day to day, right? You kick a ball, yeah, Newton works fine. But when it came down to fundamentally describing reality, it didn't work anymore. And so, with Einstein's stamp of approval, de Broglie was awarded his PhD. That thesis actually went on to win a Nobel Prize. That is the first time that a thesis has ever won a Nobel Prize. Can you imagine that? Your first kind of piece of published scientific work, and it wins a Nobel Prize? Pretty incredible. So, why? What was the big deal? Look at the de Broglie hypothesis in a little bit more depth here. So, backtracking a bit, what is de Broglie saying? He's saying that yes, since if waves are acting like particles, then who's to say particles aren't just acting like waves, right? Who's to say that light isn't a particle acting like a wave instead of a wave acting like a particle? So he said, if those light particles, those photons can act like waves, can all particles kind of act like waves? Are particles and waves really a separable thing? And so to see this, we have to say, okay, how can we tell for sure if something is acting like a wave? There's an experiment we can use. And so, do you recall, how did we say light was for sure a wave? Well, we used Young's double slit experiment, right? No way to explain that unless light is a wave. And a question here that's going to come important later, what's the necessary relationship between lambda and the slit size? Well, the slit needs to be close-ish to the wavelength, right? Why? Because if the slit is much bigger than the wavelength, right, then when you get these point sources here and they spread out again, right, well, then you just end up with no interference pattern. It basically goes back to looking like a wave, right? To get an interference pattern, you need the slits to be close to the size of a wavelength. So within an order of magnitude of the wavelength. So essentially times 10 to the same power. So if your slit is on the order of nanometers, then the wavelength should be on the order of nanometers as well. Okay, again, just because the point sources essentially recombine back into something resembling their original wavefront. Okay, so that's going to be important here. So de Broglie's hypothesis was actually a very simple argument. Okay, so by now we had equations representing the momentum of a massive particle. We've had those since the time of Newton, P equals mv, and a massless wave packet of light. That came from Compton's experiment. This is for a massive particle, like say an electron. And this is for a massless particle, like say a photon. So what did de Broglie do? He said, well, if P equals mv and P equals h over lambda, mv equals h over lambda, right? They both equal P. And there we have it. mv equals h over lambda, wavelength. You can rearrange that and solve for the wavelength of a massive particle. So we are talking about the wavelength of some particle. That statement alone should be weird to you, right? This is strange. It should make you scratch your head. The wavelength of a particle. Before all of this, waves and particles were two completely different things. Wavelength of a particle was oxymoronic. And yet, there it is in de Broglie's equation. Lambda equals h over mv. Now, just a side note here, when you're discussing a massive particle's wavelength, you must use momentums, never energies, okay? So the kinetic energy of an object is not equal to hc over lambda because they're talking about two completely different things. 1/2 mv squared is only the particle's kinetic energy. hc over lambda is the total energy of a photon. These come from momentums. They do not come from energies. There is some weirdness you can do with energies, but that is beyond physics 30. So no energy. These are not the same thing, right? Even just the fact that a particle can have different kinds of energy besides mv squared should tell you that, yeah, this doesn't work. Okay, so right now, just some weird math, right? We're just going to say, okay, de Broglie, you magnificent weirdo, let's see. So if your equation is right, you're telling me a baseball has a de Broglie wavelength. That's what we call it, a de Broglie wavelength. Okay, so that's this. This is the de Broglie wavelength. By the way, folks, this is not on your formula sheet, so you need to be able to derive this from mv equals h over lambda, okay? So you need to either memorize it or just derive it from momentum equals momentum, okay? All right, so let's see. Let's go along with de Broglie's strange ideas for a second here. So the de Broglie wavelength, sometimes it's even denoted as lambda de Broglie, equals Planck's constant over mv. See, I told you Planck's constant pops up everywhere. As you go on in your physics, you'll see it pop up more and more and more and more places. That's what happens when you're fundamentally cooked into the code of our universe. Okay. Just plugging in there, and we're going to get that the de Broglie wavelength of this baseball, yes, the wavelength of a baseball is 2.21 times 10 to the negative 34 meters. Okay, now let's return to our earlier question of what was the relationship between the slit size and the wavelength. Well, the wavelength needed to be close-ish to the slit size, or vice versa, right? So 10 to the negative 34 meters. Do you know how small that is? This is about 5 times the size of something called the Planck length. So it is bigger than the Planck length. What's the Planck length? That's, again, something for another year of your physics career. But to put the Planck length in perspective, I want you to imagine a dot that is 0.1 millimeters, which about represents the minimum thing a human eye can even see. If something has a diameter of less than 0.1 millimeters, our eyes are not capable of detecting it. Okay, got it? Take that 0.1 millimeter dot, and I want you to make it the size of the observable universe. To kind of put that size into perspective, the size of the observable universe, it would take about, okay, what's the size of the observable universe? Well, that you've just made this tiny dot. Our best estimates, our best calculations put the size of the observable universe at about 47-ish billion light years. What does that mean? Well, light traveling at 300,000 kilometers every second would take 47 billion years to just cross the radius. So it's actually double that to go from one end of the observable universe to the other. Realistically, talking about ends of the universe doesn't make sense. Observable universe is what light has had time to even reach us from. Okay, so you're going to take that tiny dot that you can't even see and make it the size of the observable universe. Now, if you've done that scaling, how big is a Planck length now? Well, now that Planck length would be about the size of the 0.1 millimeter dot originally within that observable universe. That is how small we're talking about with a Planck length. So to bring it back to this wavelength here, that's only about 5 times larger than that incredibly small Planck length. you realize why we start to see, oh, okay, that's why baseballs probably don't display many wave-like properties, right? If we were to try and do a double slit experiment with a baseball, you cannot find a slit that small. In fact, smaller than a Planck length, there is no meaningful way to talk about distance. You can imagine half a Planck length, but it's actually a scientifically meaningless concept. There is no way for us to do any meaningful analysis of something smaller than a Planck length. Some physicists actually believe that this means space itself is quantized. There is a smallest amount of space. There are little pixels that our universe is made up of. Space is not continuous. Okay? There are objectors to this theory, probably more support than objectors. Okay? In fact, the same goes for time. As you'll learn, space and time are not so different. Okay? But that there is a minimum amount of time. Time does not just flow continuously. Time is itself even quantized. A minimum tick that the universe moves forward. Okay, anyway, you see why wave-like properties would be hard to observe in anything like a baseball. However, and it was inevitable we were going to get a very small number because Planck's constant is times 10 to the negative 34. Anything with a mass even approaching a gram, let alone kilograms, is going to have a very small de Broglie wavelength. However, we can think of some particles with some very small masses that this number doesn't become stupidly small, right? An electron is times 10 to the negative 31. That's actually not that far off from Planck's constant of negative 34. We'll try it first with a proton, about 1,800 times larger than an electron, but still much smaller than a baseball. So just going to go ahead and convert that right away to joules. So we have 7.5 times 10 to the negative 3. That's, right, mega electron volts. Be careful. Capital M means mega, and mega means times 10 to the 6. I get, looks like I'm rounding, but I'm not. This is actually just what you get. Whoops, sorry, I dropped a 0 here. Okay, so calculate the de Broglie wavelength of that proton. Well, here's where students will sometimes start, okay? Remember though, what did this apply to? Photons, massless particles, okay? This is the wavelength of a massless particle, so no, okay? Energy does not equal hc over lambda. We're talking about a proton, something with mass, okay? Especially tempting because we were even given an energy. So we're going to start here, well, right? And then we realize, okay, we don't have V, we have the energy, but since this is a massive particle, we can find its energy, its kinetic energy this way, right? Mass of a proton on the back of your data sheet, and I got that it must be moving at. So now we'll take this over here. And I got that the de Broglie wavelength of this proton would be, okay, well, now we're talking times 10 to the negative 13 meters. That's approaching some physical distances that actually do kind of exist. I won't do the math on this one. You can check the example video for it. But if we decrease the mass even more to like the size of an electron, well, then we can really bring this de Broglie wavelength into something that would seem to be physically achievable. But so far, this is all just math tricks with an unproved equation. De Broglie said P and P, slap them together, right? We can't always do that. In fact, we've just talked about how you can't just do that with energy. So you should be skeptical of this right now. So the classic double slit experiment where you just scratch some glass or cut some holes in some cardboard or something like that, okay, doesn't work. The slits must be too small to be physically real, except crystals have atoms that are spaced by roughly the right amount, okay? So you have crystals that are spaced out roughly the right amount. Therefore, this experiment is sometimes called crystal diffraction rather than just another double slit experiment. It is the same idea as a double slit experiment, but we use crystals and we're looking at diffraction, okay? Or it's sometimes called the Davis and Germer experiment. They kind of stumbled upon this result while they were examining something else. They were looking at how electrons scattered off of different metals, and they found something shocking. A reminder of what the standard double slit experiment looks like. You have interference where crest meets crest, trough meets trough, right? Constructive to make a bright spot, a max, and then where trough meets crest, you have destructive interference to produce a min, right? That's how we knew for sure light was a wave until we didn't know for sure light was a wave anymore. So in crystal diffraction, Davison and Germer, they took some electrons, they fired them, they accelerated them through a voltage, right? You can see the electric fields going that way. So that's defined as what a positive charge would feel. So of course the negative charges of the electron feel the opposite and they get accelerated. Pass them through a crystal lattice with a slit size similar to this calculated de Broglie wavelength of an electron, this weird hypothetical thing that had been come up with. And what did Davison and Germer see? Yeah. Electrons acting as waves, interfering to produce a pattern of constructive and destructive interference. This is essentially a phosphorescent film. Okay, so when it makes contact with a particle, with a charged particle, it essentially gets lit up. Okay, and so you can see here, after sending a few electrons through, this is what they started to see. More and more, they started to go, oh my gosh, we are getting bands of constructive and destructive interference from these electrons, these particles. They are acting like a wave. What? The whole thing we said about the double slit experiment was that particles should just go through one slit or the other and then be done with it. And so Davison and Germer kind of went, huh? Okay, well, we're shooting a whole bunch of electrons. This is strange. Maybe something weird's happening. Somehow multiple electrons are kind of bouncing off of each other and producing this diffraction pattern. Let's just slow our electron gun down. We're only going to fire one electron at a time, okay? And then we'll see. So they said, okay, let's try this. And they shot one electron at a time at the crystal. And so what did they see? They saw pew, 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 pew. And then they let it go, shooting one electron at a time. Pew, 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 pew. One electron at a time. They still got a diffraction pattern. They were shooting one electron at a time into this crystal grating. And yet these single electrons seem to be interfering with themselves and producing a diffraction pattern. Do you hear what I'm saying? A single electron can only go through one slit. There's not even another electron going through the other slit at the same time to interfere with. So what was happening? These electrons, one single electron, was going through both slits and neither slit at the same time. Yes, one particle, one electron, was behaving as though it was going through both slits at the same time. Why? Well, quantum mechanics is a world governed by probabilities. So what are they interfering with? They're interfering with themselves. No, not one electron is interfering with another electron. One electron is interfering with itself. How is this possible? Well, an electron is described by something called a wave function. It comes from something called Schrodinger's wave equation, which essentially defines the probability of finding an object in some space. Now, even that wording is not quite true because the wave function that describes where an electron is the electron. Sounds weird. It is in all of those positions at once. Anywhere it has a probability of being, it is. This gives it its wave-like properties. So that wave function can interfere as a wave. Again, what's a wave function? So it describes the probability of the electron location, but also it is the electron. Weird, I know.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle.
So this is still just, though, a diffraction grating. So what are the relevant equation? It's still this guy, right? Where now this is the de Broglie wavelength. Or we shouldn't use it for calculations, but it's good for saying if we change one variable, what happens to another. Now, which slit are they going through? And is this even a meaningful question anymore? So remember, they are described entirely by probabilities. The quantum world is described entirely by probabilities. Okay? Einstein hated this. Einstein did not like this. I think his direct quote was something like that God does not play at dice games, right? It seemed like our universe on a fundamental level was being governed by these strange probabilities. Just wrapping your head around that is hard. If this is making you scratch your head, I don't blame you. It should. It makes the greatest physicists who have ever lived scratch their heads to this day. Countless quotes of people saying that anyone that tells you they understand quantum mechanics is lying. You cannot understand this. We can model it. We have used it so successfully to describe our universe, and yet it will probably never actually make sense, at least not intuitive sense, like 2 + 2 is 4. This seems like one of those things that you would think, okay, well, something's missing. They're going to figure it out. And yet we've tested this time and time again. Every test we've ever done of this, quantum mechanics has passed with flying colors, right? We have never observed something that contradicts this. In fact, everything we do seems to strengthen these ideas of probabilities being underlying everything in our universe. And so which slit are they going through? Okay, so there's a probability of them going through slit A, slit B, or neither. So guess what? It's doing all of those things. It's going through slit A and slit B, and it's not going through either slit A or slit B because the probability of those things happening is not 0. And so that gives us this wave function, this probability distribution. That wave, because that wave is going through both slits and neither slit, it can now meet up with itself and interfere. Okay? Bonkers stuff, and yet real stuff. Through both and neither slits. They are this wave function. Okay, I'm going to show you another part of the video and then we'll come back and talk about it.
But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
When physicists saw this, they said, it seems like for this to happen, these electrons have to be going through both slits at the same time, right? How can that be true? How can that be happening? So they said, okay, weird. Let's just look at one slit. We'll detect the electrons that go through, and then we'll know, well, they went through that slit or they went through that slit. So they did that, right? And as you saw in the video, well, they went back to behaving like particles. As soon as we did that, they went back to behaving like particles. Why? I want you to think about the wave function. The wave function, again, describes the probability of finding an electron in space, right? Well, if we observe that electron, we now know where it is. And so something happens that we call collapsing the wave function. As soon as we know where it is, we've collapsed the wave function. It no longer has a probability of being somewhere. It is somewhere. And so does it still have a wave function? Yeah, but the wave function is localized in one place. So I'm not breaking what I said earlier about the electron being the wave function. It still is. It's just now its wave function isn't very interesting. We've collapsed it. It's now localized in space. It's a particle again. Okay? It can't have wave-like properties because we've destroyed the probability of it being anywhere else simply by observing where it actually is. And so its wave-like properties disappear. It behaves as a particle again, and we get those two bright bands of electrons, just like we would have expected them before all this weirdness. Right? We've collapsed its wave function so that it now says, okay, it has a probability of being here where you saw it. You ruined the fun, right? And therefore, it behaves only as a particle again. Now, worth mentioning here is the idea of Heisenberg's uncertainty principle. So essentially, de Broglie, we saw now that particles have wave-like properties. So you can think of putting a particle in a box. And if it's a wave, the stable way for a particle to be in a box, as we learned in physics 20, is for it to be in a standing wave, right? You must have a node at both ends. So that's a stable configuration. This is going to become really important when we do the quantum model of the atom. So it's good to see it now. Okay, that's a stable configuration. So remember, what is this wave? It's the probability of an electron or some other particle being at some point in space, right? Now, how could we be more sure of where it is? Well, make the wavelength smaller, right? Make the wave smaller. So you could squeeze in the size of these boxes, squeeze them in, making the wavelength smaller and smaller and smaller, being more and more sure of its position. But remember, momentum is equal to h over lambda. So the smaller you make its wavelength, the more sure you are of its position, the less sure you are of its momentum. Okay, this puts a fundamental limit on how much we can know either of those quantities. We can know its position with a great deal of certainty if we accept that we will have no idea about its momentum and therefore its velocity. And vice versa. We can be very sure of its momentum, very sure of its velocity, but have no idea about its position. I am not referring here to the limitations of our equipment. It's not that we just need to develop better equipment. We will never, given a billion years, unless something radically changes in our understanding of the universe, we will never, ever be able to be infinitely certain about the particle's position and the particle's momentum at the same time. This is known as Heisenberg's uncertainty principle. It puts a fundamental limit on how well we can know the properties of it. I actually really like this picture for kind of visualizing the uncertainty principle. So again, if we're modeling quote unquote particle, but we're looking at its wave properties, right? Well, we can be really sure about its momentum by just imagining it as this one wave, by just imagining it as this one wave with this one wavelength, this one frequency, right? By this formula. So if there's only one wavelength, then yeah, there's a momentum. We know it pretty well, okay? However, where is this particle? Remember that this wave is the probability of finding that particle at that position. Again, the wave is the particle. The particle is described by its probability of being found in space. Yes, it's weird, but that's how it works, okay? So there's a probability here, probability here, probability here. This one wavelength, right, extends on and on and on. And so there's kind of all of these probabilities, infinite, in fact, probabilities of where it could be. So if you were to ever be infinitely sure of its momentum by having just this one wavelength, you would by default be infinitely unsure of its position, because the crests are where it is most likely to be, and there are an infinite number of them. Now, we could be a little bit more certain of its position by adding a bunch of waves. So what we're doing here is we're adding waves. Some look like this, some look like this, right? Some look like this. And we just add them all together until they constructively and destructively interfere in all the right places to give us this little wave packet. Okay, and notice how now there's a smaller delta x, a smaller uncertainty in its position. However, what did we do? We introduced a whole bunch of wavelengths. So the uncertainty in our momentum now is now larger, right? We're less sure of the momentum of this wave because we're less sure of its wavelength, because it's made of many wavelengths. Now we can get even more certain of the particle's position by just adding more and more waves to constructively and destructively interfere in the right ways, where you get this, right? You just get destructive interference all along here, destructive interference all along here, and then this nice little place of constructive interference where we say, okay, the probability of it being here is good, the probability of it being out here is very low, so we know pretty well where it's got to be. Except, what did you do? You added even more waves with different wavelengths, increasing your uncertainty of your momentum. So Heisenberg's uncertainty theory is usually represented this way. The derivation comes from wave equations. And they are wave equations, okay? So the uncertainty principle is actually fundamental to wave behavior. Again, this has nothing to do with our measuring equipment. It is a fundamental part of wave mechanics. We cannot be infinitely certain of either the momentum or the position, and the more certain we are of one, the less certain we are of the other. There's no way around that. So let's do it. This is a theory example, so we'll do this one, okay? The more math examples will be in the other video for this topic, but let's just see here, okay? Thinking back to scientists and explanations. So the explanations above are based on light having only wave, only particle, or both wave and particle, or neither wave nor particle. So Einstein's explanation of the photoelectric effect requires light to travel in bundles. Well, that bundles, right? Einstein, photoelectric, that's particle-like behavior. Young's explanation of the observation from double slit experiment requires light to interfere with itself. So interference, that's a property of waves. So already we can kind of see the answer. De Broglie's explanation of stable atomic energy levels, looking ahead to unit D a bit here, requires electrons to exist as standing waves. Well, there it is, right in the name, waves. So of course, these describe something with both wave and particle properties. All right, so in summary, okay, summary of the de Broglie bomb I've dropped on you today. Wave-particle duality is a two-way street. Okay, you can't have particles acting like waves, but then say waves can't act like particles. Even just saying that particles act like waves means that waves act like particles, right? Light is, I guess you could say it's both a particle and a wave, but it's also kind of neither a particle nor a wave. It can have properties of either depending on how it interacts with its surroundings. Same goes for an electron. It's not a particle, it's not a wave. It can have properties of both depending on how it interacts with its surroundings. Truthfully, nothing is actually a particle or a wave, including you, okay, including a baseball. This entire concept of particles and waves is an old world idea. It belongs to classical physics. Particles and waves are not these easily separable ideas where you put them in the particle box or you put them in the wave box. All things have properties of both. It's just that on our day-to-day level, we can kind of separate them into particles and waves based on their macroscopic behavior. But at a fundamental, universal level, All things have properties of both. This is a concept known as wave-particle duality. All things are wave particles or particle waves. You can't separate these ideas. So just on our day-to-day life, they're not really apparent unless you count the tons of technologies that actually apply this quantum mechanics. It's in your phone, it's in MRI machines, it's in quantum mechanics is everywhere. Here's kind of a visualization, the best we can do. Of course, this stuff is beyond our human ability to picture it really, but this is kind of how we visualize it. Sometimes you say it's got a wave-like aspect, right? It acts like a little packet of waves, but it also has a particle-like aspect. So there's a ball that's an electron, if you want to think of that cutesy little idea of an electron, but you can also think of the electron as a wave function traveling through space. Again, if this stuff did not do such a great job of describing our universe, I wouldn't blame you for throwing it all in the garbage and saying that's a bunch of nonsense. Okay? And like I said, though, for 100 years now, all we've ever been able to do is strengthen this theory, never once refute it. So science fact can really be stranger than science fiction. We live in a weird universe, but it is a fascinating universe. All right, and with that, we wrap up Unit 3. What a journey we've gone on, eh? Did you think we'd get here when we first started talking about the color of a hot object? Led to some pretty revolutionary ideas. We've gone through a trip here. So with that, you can check the Google Classroom or the agenda for the practice work that goes with this. And I'll be making, of course, the example videos to go through the more numerical examples in this section.